Imagine a world where after a long, hard trail ride, you can simply come home, roll your bike next to the wall, push a button, and voila, out of sight, out of mind until the next ride. Imagine an electric bike lift. This is a real-world problem that we can solve by scaling it down to a workable level. We've designed a kit for this very purpose, a kit that can be used in the classroom or at home to model real-world conditions at a fraction of the cost in a fraction of the time. Our kit is perfect for professors and students. As a professor, this kit gives you the power to teach physical concepts without the textbook, to give your students a new level of insight and understanding not achieved in the mundane classroom, to really teach your students in new and exciting ways, to show the importance of safety factors in design, to experience learning by different means. As a student, this kit imparts real-world knowledge that gives you a leg up in the academic community, a way to interact with your professor that is far more intellectually stimulating than sitting in a hard chair, to learn mechanics and electrical concepts by doing, not reading, to see the importance of safety in your design, not just to be told that it's important, the ability to create a system and learn from that creation instead of listening to a long, boring lecture. Using this kit will teach students a large scope of technical knowledge. First, we use an Arduino Uno microcontroller. Students will learn how an Arduino works and how to program them. This serves as a great introduction for anyone interested in embedded systems or robotics. Students will learn about semiconductors, how the properties of a component with variable conductivity can benefit them. Students will need to use transistors to amplify their input current to supply their motor with enough energy to lift heavy loads. How the use of a diode is like a one-way valve for current. Students will learn the importance of diodes to protect their transistors from harmful feedback. Students will learn the basics of DC motors, what makes them work, how efficiency is determined, how to manipulate circuits to achieve different results with a DC motor. Students will learn about the use of capacitors to give extra charge to a circuit, or resistors to limit current in a given system. Students will learn about potentiometers and how they can use them to control the speed of their motor because of the potentiometer's inherent variable resistance properties. Students will learn how to wire a DP-DT switch to reverse the polarity of their motor to both raise and lower a load. Our kit will teach students about simple mechanics, how the use of gears can take a low torque, high RPM motor and convert its energy to a low RPM, high torque output. Students will learn about pulleys and how they can be used to gain mechanical advantage, how pulleys can be used to take a small force and move a large mass. This kit is the answer to taking physics concepts from obscurity and illuminating them through real-world analysis. Our prototype is built with output power in mind. We wanted to see how much total weight we could lift. However, our kit is built with flexibility in mind. One could build a proto for max weight lifted, or moderate weight with moderate efficiency, or with only efficiency in mind, and every combination in between. That's the core idea of this kit, the freedom for the user to choose their goal. In our prototype, we used a 3-to-1 gear ratio to maximize torque and decrease RPMs. We used a guide to coil the thread uniformly in the center of the axle to avoid friction from the thread building up and rubbing on the sides. We used a 4-pulley system to give us a 4-to-1 mechanical advantage, focused towards maximal lift force. We used thread to decrease friction between the pulleys and to avoid an ever-increasing radius on the drive axle. We used a transistor to amplify current, a diode to keep it safe, and a potentiometer to control speed. We used a DP-DT switch to allow the motor to both raise and lower the weight. The Arduino board supplies the energy, and the potentiometer controls the speed. All of these components combined gave us a system capable of lifting 240 grams with a maximum efficiency of 51%. In any project, life skills are important to have and even more important to implement. Critical thinking was vital to our project. For example, we noticed that the string we were using was coiling rapidly and increasing our drive axle diameter. We believed this was affecting our torque. We decided to swap out the string for thread, which would result in a smaller diameter when coiling, thus increasing torque. It would also lead to less friction loss through the pulleys due to reduced surface area. Open to new ideas, we made the change and measured an efficiency of 51% that was previously only 20%. Our max lift went from 117 grams to 240 grams, all due to critical thinking. Reflective thinking allowed us to re-examine our prototype intelligently. On our first proto, we were getting poor performance results, and we asked the question, why? We then started thinking of areas where we were losing energy. We realized better pulleys, a guide post for the thread to coil neatly, and bearings for our drive shaft would decrease friction loss and result in better performance and a better prototype. Knowledge construction was crucial to our prototype success. We needed a lot of knowledge that we did not possess. For example, how a DC motor works, transistors, mechanical advantage, and potentiometers, to name a few. Teamwork was another area that was vital to our project. Each team member was supportive, encouraging, accepting, and respectful of each other's ideas. We all worked toward a common goal, each member doing their best to contribute intellectually to the project. Meetings were well organized and productive due to each member being open to new ideas and employing critical thinking to solve problems. We instituted an open forum for communication, every idea to be heard and considered. At each meeting, a team member would present data and ideas. The team would discuss, and then conclusions would be made. For example, we thought changing the drive shaft diameter might result in better efficiency. The group decided to try it and found that a larger diameter was actually detrimental. But this showed us that our original diameter was better and why it was better. We feel that applying these life skills to our project was critical to our success. And there you have it, a bike lift kit for professors and students, created by students. Thanks for watching.